This text is the formal recommendation from the ITUT, the United Nations Agency for Information and Communication Technologies. They define the Internet of Things as a global infrastructure interconnecting physical and virtual things based on interoperable communication technologies. Public perception usually frames this concept around smart home gadgets, thermostats, doorbells, or refrigerators. But at the industrial level, we are dealing with the automation and remote management of critical municipal, national, and global systems. This diagram illustrates the industrial architecture, mapping physical objects on the left directly into a digital world on the right. At scale, this happens simultaneously across millions of independent nodes. If all data is forced through a single gateway, the system bottlenecks and fails. Industrial IoT represents a structural transition from isolated tools to a planetary-scale distributed nervous system. The modern smart grid provides the perfect model to understand the physical demands of this architecture. Electrical substations and distribution centers represent the absolute extremes of scale and environmental hostility. This chart contrasts grid designs. The top illustrates the legacy model, centralized generation pushing energy outward unidirectionally. The bottom shows the 21st century shift, distributed generation, where energy and information flow bidirectionally. Operations centers need constant, real-time data returning from millions of edge nodes. Gathering that bidirectional data requires massive sensor networks deployed directly onto the hardware. This introduces severe physical constraints that traditional cellular infrastructure cannot overcome. To understand why the telecommunications industry had to invent an entirely new standard to handle this data, we have to look at the exact physical barriers that cause 4G and LTE to fail at the industrial edge. This graph tracks the historical cost and size reduction of computing. We started with massive, isolated mainframes, gradually scaling down into personal computers. Miniaturization and exponential cost reduction pushed computing hardware past mobile phones, directly into everyday physical objects, creating universal smart things. This conceptual model demonstrates how that hardware scale applies to the smart grid. Cheap, miniaturized sensors are now deployed at every point in the electrical chain: bulk generation, transmission towers, distribution lines, and individual customer endpoints. Routing data from that many devices creates an immediate logical bottleneck. The grid mandates the use of IPv6, an internet protocol capable of providing the billions of unique IP addresses required so that every individual sensor can communicate directly without relying on network address translation gateways. However, IPv6 only solves the software side of the scaling problem. Addressing millions of devices logically does not solve the physical challenge of actually transmitting a radio signal to them. Industrial edge devices are deployed in highly hostile environments. They are frequently buried underground, installed deep inside thick concrete basements, or encased in steel boxes. These environments introduce two critical radio frequency limitations: shadowing, where large obstacles block the signal entirely, and path loss, where the signal naturally weakens as it travels through dense physical material over distance. Traditional, high-bandwidth cellular signals, like the 4G networks used by smartphones, operate at frequencies that are physically incapable of penetrating these dense barriers without suffering severe degradation. The standard telecommunications solution to severe path loss is to simply increase the transmission power. For tiny, self-contained edge devices running on internal batteries, dedicating massive amounts of energy to blast a signal through concrete is physically impossible. To achieve extreme signal penetration into deep industrial environments, a network must sacrifice high data speeds and traditional cellular protocols. The inability to use high-power transmissions brings us to the core logistical constraint of the grid: replacing batteries. Paying technicians to manually locate and swap batteries on millions of distributed sensors is economically unviable. The hardware must run for years untouched. Standard cellular networks require devices to constantly ping the local cell tower to maintain an active connection. That continuous handshake protocol will destroy a small sensor battery in a matter of days. These specific limitations forced the industry to define an entirely new network classification. This slide breaks down the requirements, starting with LP, or low power. The device must be able to function for many years on a single battery charge. The second half of the mandate is WA, or wide area. The network must operate over massive distances and successfully penetrate the dense shadowing and path loss zones that render traditional networks inoperable. The smart grid's physical realities exposed a massive void in existing telecommunications. The world needed LPWA networks, and multiple organizations immediately raced to build them. Recognizing the multi-billion-dollar scale of industrial IoT, technology companies and telecom standards bodies began a fragmented race to establish the dominant LPWA protocol. This chart outlines the resulting complex taxonomy of LPWA standards. The market split rapidly between closed, privately owned technologies and open, collaborative standards. On the right, we see proprietary technologies like LoRa and Sigfox, which require distinct hardware and unique network deployments. On the left are the open standards developed by international bodies like the IEEE and ETSI. The most critical branch for global infrastructure is 3GPP, the consortium responsible for managing global cellular standards like 3G, 4G, and 5G. Their goal was to adapt the existing ubiquitous cellular tower infrastructure specifically for IoT. By building within the 3GPP framework, the telecommunications industry ensured that IoT devices could utilize established cellular tower coverage worldwide. This standardization allowed for a globally interoperable network that integrates directly with current utility operations. The 3GPP answered the LPWA mandate with specific cellular categories. The yellow box highlights their primary solution, User Equipment Category M1, known commercially as LTE-M. LTE-M solves the power problem by overriding standard cellular behavior. It utilizes specialized protocols like eDRX and power saving mode to force the radio into extended sleep cycles, ignoring the network entirely until it has critical data to send. Despite spending most of its life dormant, when an LTE-M device wakes up, it still supports the fully bidirectional information flow required by grid operations to adjust loads and clear faults. LTE-M is a re-engineered protocol layer. It strips away the broadband speed we expect from cellular networks, specifically prioritizing extreme physical penetration and minimal energy consumption. It is the precise architectural solution required to operate the industrial edge.